Sample problem using the common ion effect. Calculate the solubility of calcium fluoride in grams per liter in pure water, 0.15 molar potassium fluoride solution, and 0.08 molar calcium nitrate solution. The solubility product for calcium fluoride is 3.9 times 10 to the minus 11. So I'm going to show you how to solve each part here on this slide. Part A first, then part B, then part C. And then I'll slowly go through the next several slides so that you can see the worked out solution. But try this on your own first, starting with part A. We need to know what is the solubility in grams per liter in pure water. So let's start with our dissociation of calcium fluoride solid into calcium ions and fluoride ions. And let's write a general Ksp expression. The concentration of the calcium ions times the concentration of the fluoride ions squared. Okay. In pure water, we don't have to worry about any initial concentration or given concentration of calcium ion or fluoride ion. We don't know what those concentrations are, so we'll just call them X. So the Ksp, 3.9 times 10 to the minus 11 is equal to the calcium ion concentration. So that has a coefficient of 1. So let's just call that one X. And then the fluoride ion concentration has a coefficient of 2, so there'll be twice as much fluoride as there is calcium ion. So we have to account for that. We'll call that 2x squared. And so we get 4x cubed here. Okay, so 3.9 times 10 to the minus 11 equals 4x cubed. So let's solve for x. And x is our concentration of calcium ion, which is also the lowest mole ratio. So that'll also be our, in this case, we're going to do molar solubility and then find it in grams per liter. So I solve for x here. I get 2.14 times 10 to the minus 14. Now this is moles per liter. And I need to multiply by the molar mass of calcium fluoride, which is 78 grams per mole. That gives me a molar solubility of 0.0167 grams per liter. 0.0167 grams per liter. All right, so that's the solubility in grams per liter of pure water. Now in parts B and C, we're going to add a common ion and expect the equilibrium to shift to the left. So we should get a solubility that's much less than 0.0167. So let's go ahead and move on to part B. I'm going to keep some of this the same since the general dissociation isn't changing and the Ksp expression isn't changing. But in part B, we're told that we're trying to dissolve calcium fluoride in a solution that already contains fluoride. So the biggest thing here is that we're given our concentration of fluoride, 0.15 molar. Okay? So let's find our solubility. So Ksp 3.9 times 10 to the minus 11 is equal to, we don't know this calcium ion concentration. The coefficient is 1 though, so let's call that X. Now we know this concentration of fluoride, right? Because this potassium fluoride is going to dissolve completely. And so we have a very high concentration, 0.15 molar fluoride ion. And we need to square that. So we solve for X here. And we get 1.73 times 10 to the minus 9. Now that's moles per liter. Now in this case, it was calcium, but again, that's also the ion that's in the lowest mole ratio. So that's also our molar solubility. But again, we need to multiply by the molar mass of calcium fluoride, 78 grams per mole, to get our solubility in grams per liter. When we do that, we get 1.35 times 10 to the minus 7 grams per liter, which is much, much, much less than our initial solubility of 0.0167 grams per liter, several orders of magnitude less. Okay, and then finally part C. So let's clear some things here. So in part C, we have a solution of calcium nitrate. So something that contains the calcium ion, right? Because that'll dissolve completely. So what we're saying here is that we know that our calcium ion concentration is 0.08 molar. Okay? So let's see, Ksp 3.9 times 10 to the minus 11 equals 0.08. Now we don't know F, but we do know that whatever the F minus concentration is has to be twice the calcium ion concentration. So we'll call that 2x squared. Okay. Here we just have to solve for x. And when we do that, we get 1.1 times 10 to the minus 5. And this is a concentration in moles per liter. Okay. And that is it'll be a single x, right? Since I accounted for the 2 here, this single x would be my lowest mole ratio. Okay. So I've already taken care of that. And so now I just need to multiply by 78 grams per mole, molar mass of the calcium fluoride, to get my solubility in grams per liter. And I get 8.61, or 8.6, I guess, times 10 to the minus 4 grams per liter. Okay. All right, so I'm going to just go through the next 3 slides that show you a worked out solution for parts A, B, and C, in case you missed anything that we wrote down. So here's your solution for part A. We said the solubility was 0.0167 grams per liter. Your solution for part B, 1.35 times 10 to the minus 7 grams per liter. And part C, 8.6 times 10 to the minus 4 grams per liter. And then just a summary of the problem. So recall from the common ion effect from our discussion in our acid-base equilibria that adding a strong electrolyte to a weakly soluble solution with a common ion decreases the solubility, right? So if I have a solution that contains an ion that's here already, my equilibrium is going to shift this way, decreasing the solubility. And that supports the mathematical results we got. Like in pure water, we have orders of magnitude larger than we have when there's a common ion in the solution. And these results support Le Chatelier's principle that increasing a product concentration shifts the equilibrium to the left and decreases the solubility.